Good morning, all. I'm Larry Olson, President and Chief Engineer of Olson Engineering and Olson Instruments. It's my pleasure to give part of our August webinar, along with Patrick Miller, our NDE Manager and Senior Engineer. You'll see Pat Miller in a bit. As we'll share the talk, he'll do the first 2/3 and I'll do the last third. Today's topic is on the lightweight deflectometer for quality assurance and compaction of road base and subgrade. So this is like a lot of things, a 30-year-old newer device that is now starting to be used more in the United States as people are getting more interested in changing from the nuclear density gauge compaction quality assurance approach to lightweight deflectometer for the simple reason that modulus and stiffness matter. So with that as a bit of an introduction, we will be posting, as we do with our webinars, this online within a few days to at most a week on our website at olsonengineering.com under services, under training, under webinars. And so you could view the video again if you'd like to. There will be a question and answer period at the end. We think we'll have plenty of time today to go through this. We're going to also attempt a live demo, which should be interesting, as live demos always are. So Pat will be running a live demo of the lightweight deflectometer. So with that as a bit of an introduction, I'll let Pat come over and say hi, and then he can stop the video and give the PowerPoint.
Good morning. As Larry mentioned, I'm Pat Miller, NDE Manager and Senior Engineer here at Olson Engineering. I have a lot of experience with the lightweight deflectometer, going back to my master's research at Colorado School of Mines and continuing here with Olson. So I'll be going over some of the basics and then I'll turn it back over to Larry at some point. Okay, so just to give you a quick overview of the lightweight deflectometer, the unit itself is approximately 60 pounds total, including the drop weight. The drop weight itself is about 22 pounds or 10 kilograms. There's also two optional add-on weights that can add 5 kilograms each. So you can bump that up to 15 kilograms or 20 kilograms if you're working with very stiff soils. Our unit has a nominal applied force of about 1,400 pounds based on the standard weight. And the impact duration is about 17 milliseconds. We have plate diameters of 100, 150, 200, and 300 millimeters, or 4, 6, 8, and 12 inches. And we do have an optional set of geophones, 2 geophones external to the device, spaced at 1 foot and 2 feet away from the center of the plate to measure deflections. To operate the device, it takes one person. It's 1 to 2 minutes per test. Our device interfaces with a Windows-based tablet. It's a touchscreen handheld tablet. We prefer the Dell ruggedized tablet that's shown there in the picture. It's great in the sunlight, has the built-in GPS. We're a fan of that unit. The device is primarily used for quality assurance of soil compaction. Basically, you strike a circular plate with the following weight. You impact that force into the soil, and you measure the displacement of the plate resulting from that force. From that force and the displacement, we can calculate the stiffness of the soil, as well as Young's modulus if we assume a Poisson's ratio and unit weight. You can do measurements on road base, sub-base, and subgrade fill. You can also do quality assurance of cement stabilized or lime stabilized soils by testing before and after the stabilization to see the increase in stiffness or modulus. Additionally, there's applications to railroad ballast or coarse crushed rock, and that's kind of an area of ongoing research. Here's a picture of our Senior Vice President, Dennis Sack, running the device on a project site here in Colorado. Again, it's 1 to 2 minutes per test. It's a one-person operation with the tablet notebook. The data acquisition is a separate box that you can wear on your belt. We often like to sling the tablet over our shoulder on a strap. One of the important parts is kind of seating the device. You kind of twist the device in with the 2 handles on the plate, twist that into the soil to make sure it's well seated. Then perform your 3 seating drops, and then typically 3 measurement drops. Our device has the option in software you can run as many as 12 drops if you would like. Additional drops are sometimes helpful on coarse material where there's higher variability. Here is an example of some data from the LWD. The top plot shows the force time history with time on the x-axis, force on the y-axis. This shows a maximum force of approximately 1,450 pounds over that approximately 17 millisecond pulse duration. The lower plot shows the displacement, which is we obtain from integrating the measured velocity that we have from a geophone embedded in the device. We're measuring the velocity of the plate itself, integrating that to displacement. This example, we have approximately 25 thousandths of an inch displacement, resulting in a stiffness of about 58 kips per inch and a modulus of about 7.9 KSI. The modulus equation is based upon Boussinesq's theoretical solution to a static load applied through a rigid circular plate on an elastic half space. Basically, this schematic here shows the kind of the breakdown of the theory. You have the maximum plate deflection, you have the maximum load or force from the impulse load. Those two, force over the maximum maximum force over the maximum deflection equals the stiffness. We plug that stiffness into the second equation there. It shows Young's modulus equal to twice that stiffness times 1 minus the Poisson's ratio squared, all over the factor A, and multiplied by R, which is the radius of the plate. The A factor is the contact stress distribution factor, and that's based on the soil type. We'll get into that here in a minute. I'm going to pause there and go ahead and do the live demo so you can see the device in action. Let me switch to, this is a live screen of our software. I'll go ahead and initiate a test. Well, let me run through the software real quickly here. On the far left, you have what we call our data parameter window. This is where we have our two channels turned on. The first channel being the force with the calibration number in there. The second channel being the built-in geophone with the calibration number in there. Channels 3 and 4 for those radio external geophones. We don't have those today, but that's what they're there for. Also, you can set the spacings of those, the distance of those two geophones, as well as the calibration. You can set those extra geophones would be used for if you have a two-layer system that can help you with that analysis of that lower, deeper layer. That's also an area of ongoing research. You can set the number of drops, so I'll go ahead and drop that down to 3 drops. You can set your Poisson's ratio, whatever you want to assume that to be. You can enter your moisture content if you're measuring that by other means. And you can also set your density of your soil if you know that from your proctor test or what your soil sample is. The soil type, this is that A parameter that I discussed briefly. We'll come back to here in a few minutes. You can set it to be a cohesive soil, clay, with a value of 4, kind of a mixed soil type of some clay, some sand, or a cohesive list soil, a sand material, which is the lowest value there, the A parameter. You select your plate diameter. Today we're using an 8-inch plate diameter. So once you kind of have your basic parameters set, you can hit the Start DAC button. In the top, you can path to wherever folder you want to save your data. You can give your data a root name, and the suffix will just increase numerically as you take more data. Has the date. You're welcome to type in any notes if you want to specify a location. You know, this is 2 feet from the curb or near a manhole or whatever kind of notes you want to put in there for field operation. Over on this side, we have the lift. If you're testing, you may be testing the same spot at multiple lifts of soil preparation. So you may want to distinguish by lift. Again, you have another location field here where you can make a note. You can also do stationing. So you can put in the station, 100 plus 50 or whatever your station may be. It also does grab the latitude and longitude from the tablet. So that's that information's built into the file. It's not the real precise GPS, but it is based on the tablet GPS. Once I'm ready, I just simply hit OK. And you'll see there in the status of the software that says waiting for data. Okay. And now you can see we have the device sitting here behind us. I have the weight currently in the up position, plate on a couple rubber pads. We're on a carpeted floor, so the data is going to be a little, look a little funny here on the carpet. It's a funny response. Our device is somewhat unique in that we do have a safety feature. We have a little extra button here, so that we created that so that the release requires 2 hands. We felt that the most common, the most possible way of injury would be to grab the shaft with one hand while you accidentally release the weight, the drop weight with the other hand. So we made this a 2-handed release mechanism. The weight additionally has a little locking feature. You can twist the knob and lock that weight off, and then it can't be dropped. So once we release the weight, it's a simple little button here that needs to be pushed. So I prefer to squeeze it, pinch it with my left hand, operate the lever with my right hand, and then catch with my left. So once you get familiar with the operation, it's very simple to use. And the data will just pop up there on the software, as you can see, with each drop, and then it resets itself and waits for the following drop. So one additional drop to do. So saving complete, and then it shows you your data from that record. That presents your max force, your max displacement, your stiffness, as well as your modulus. If you're going to transport the device, or if you're done using it for a time, I prefer to put the weight in the low position, and you can also lock that weight off if you want. This is the data acquisition box. It's about maybe 4 by 5 by 1.5 inches. It's got the belt clip on the back, and it's wired to the computer or tablet as well as the LWD. So I prefer to wear this piece on my belt. Again, sling the tablet over my shoulder, and I can walk around with the unit pretty easily. We also have a small cart that goes into the unit to drag it around the site. Nice, large pneumatic tires. We have the D handle on the top to make the dragging easier, but that D handle can be easily removed if you prefer just to have the straight bicycle grip handle. So let me get back to the presentation here. So a few current industry issues that are still kind of being worked through is this stress distribution factor, that factor A. That's used in all the algorithms to calculate the modulus value. And depending on what you set that A value to, you're going to get significantly different modulus values. Even if you are using the same A value, different devices will also produce different modulus values. And that's just due to the complex nature of soil behavior, especially under dynamic loading. And it's also due to small differences in the devices themselves, such as the weight of the device, the impulse force level, and the impulse force duration. It also has to do with the method of response measurement. Some devices use an accelerometer versus a geophone, and there's also devices that use a geophone that contacts the soil directly through a small hole in the plate. So these differences kind of led to the development of 2 ASTM standards. So there's ASTM E2835 from 2011, and that standard involves devices measuring deflection of the load plate itself. Our device falls under that standard. However, we feel that we exceed that standard by also measuring the applied impact force. The other standard, E2583 from 2007, involves devices that measure the soil displacement through that small hole in the plate with a little plunger, spring-loaded plunger. And those devices also are required to measure the force applied to the plate. There's an current standard in development that involves LWD testing on laboratory compaction molds in order to relate the laboratory compaction curves to the LWD measurement values. And Larry Olson will get into that discussion here in a few minutes in the presentation. I was going to briefly cover a little bit more regarding this A factor, going back to the research I did at the Colorado School of Mines under Professor Mike Mooney. One of the things we did in our research was to vary both stress cells and strain gauge sensors in soil beneath the LWDs to try to characterize stress and strain in the soil underneath the device. So here you see a picture of some earth pressure cells on the left and some modified LVDTs on the right that we use to measure strain. We buried the earth pressure cells and strain gauges at different depths. We tried to stagger those so we didn't have any shadowing effects. We did multiple different soil profiles, one that was just pure clay, and some that were sand over clay and different thicknesses of sand. And that would be to replicate a subgrade going in over a native clay soil. Now, one of the interesting things here is Terzaghi theorized that a rigid circular plate would produce a different stress distribution depending on the soil type. So he theorized that an inverse parabolic distribution would occur on cohesive soils or clays. A parabolic distribution would occur on cohesive list soils or sands and gravels, and a more of a uniform distribution would occur on soils having a mixture of those characteristics. You can see the resulting A factors there on the right, and depending on which A factor you use, you would get modulus values varying from up to 170% from one another. So we measured the stress in the soil at different depths in the different profiles, the clay, the sand over clay, and the thicker layer of sand over clay. This gives you an idea of what those stresses look like. They're very similar to the load curve we see from the device itself. The three different lines on each plot are the different earth pressure cells at different depths in the soil. And so the really interesting thing about this study was that when we compared this to the theory of elasticity, looking at the increase in stress at depth due to circular plate loading, we found that indeed the data from the sand, the thicker layer of sand, matched more closely with the parabolic distribution, where the clay layer matched more closely with the inverse parabolic distribution. So this kind of implies that indeed that the soil type really has a big influence on that stress distribution and that A factor. And that's why in our software we let the user select that A factor, and we kind of have the helpful hint there, whether sand, clay, or a mixture. So depending on what type of soil you're testing on, you can select the A factor that's going to be the most appropriate. So why would we want to use an LWD for quality assurance and quality control of compaction? One of the big things is people would like to move away from the nuclear density gauge. The nuclear density gauge has been great over the years, but there is a lot of costs associated with training, licensing, certification, the storage of the equipment, the shipping, the handling, calibrating the equipment. All those, all that paperwork involved with those devices is burdensome to the DOTs. The LWD device is commonly used in Europe and other parts of the world. And also that the current practice really leads to a disconnect between the quality control and the pavement design. The designers are using modulus to design, where we're going out there and doing quality control based on density. And while they're related, they're just not the same thing. So why not measure modulus in the field as a quality control, which is the thing that's going to be used in the design also. And it's also the biggest contributor to pavement performance. Here's a photograph showing our calibration block. That's myself there standing up on the block. So it's a large concrete block in order to make kind of an immovable object to calibrate against. We calibrate the load cell with a reference load cell. And we really wanted to put that load cell in the device to measure that force every time. Research studies have shown that even with steel springs, that impact force may vary up to 10%. And that could be due to the angle of the shaft, friction on the shaft and drop weight, different characteristics there, the temperature even. So by measuring that force every time, we know that we're getting the right number every time. We also use 3 potentiometers to calibrate the displacement of the device on the calibration stand. And again, we wanted to use a GFO in our device to really ensure we're only going through one integration to get to displacement. Some of the other devices that use accelerometers have to do a double integration. And it's not a huge source of error, but it is a source of error that we felt we could eliminate and get the most reliable and repeatable device. The other unique thing about our device is we put the damper spring, it's a steel spring, is actually embedded in the drop weight. We like using steel rather than a rubber or urethane because it's less temperature dependent. And we really like putting that spring in the weight itself because it really creates a clean impact to the plate, and then it just leaves, that impact leaves. You don't have any kind of rebound loading on the device itself from some sort of spring capture or anything attached to the load plate. Here's photographs of the displacement calibration. We have kind of some arms there. We put 3 potentiometers equidistant around the plate to measure the deflection of the plate and account for any rocking. And we vary the thickness of the rubber pads beneath the plate to get varying displacement levels to develop that calibration. So just to cover some key features of our device, most of which I've already mentioned. Our device designed and manufactured here in Wheat Ridge, Colorado. It is a durable, rugged stainless steel and aluminum design. So our device, the plate, the hubs, the rod, the weight, they're all stainless steel. There are some wear parts. We use some bushings in the weight and some impact plates at the bottom of the weight, but those are all the high molecular weight polyethylene bushings. They're cheap and they're easy to replace, and those can be done when the unit's in for calibration. Our shaft is split in the middle. That's just for ease of storage and transportation. So it comes apart and we packs it in cases, makes it easier to move around. Again, we have that safety latch mechanism I mentioned to reduce the risk of injury. And that's a good picture of the cart. And so that's our cart's very minimal. It just kind of slides in under a little ridge in our hub and lifts the device. And then it has a little bracket there to cradle the rod. You kind of put your foot on it and rock it backwards, and you have that D handle. You can push it or pull it around the site very easily. So there have been some early implementation methods proposed by different states. Minnesota DOT used a control strip method. So at the beginning of the compaction stage of the project, you would establish a small control area in which the moisture content and compaction levels would be very well controlled and executed. And then you perform that LWD testing on that control strip area. And that would kind of establish that pass-fail criteria. So once you had those cutoff values, then you could perform your LWD testing throughout the whole project using those target values from your control strip as your pass-fail criteria. We should mention again that moisture content's important. It affects the LWD results. If the soil gets really dry, it tends to get stiff as well, even if it's not well compacted. So you definitely have to account for moisture content. Ideally, you're performing the LWD test at that moisture content that you're doing your compaction at. A second implementation method proposed by the Indiana DOT, similar control strip method. This goes into a little more detail. They perform 4 passes with their vibratory roller. They perform the 10 LWD tests, perform a 5th pass with the roller, perform 10 more LWD tests at the same locations, and then look at those differences between those LWD values. If those values were less than the 0.02 millimeters as far as deflection goes, then that was considered the maximum allowable deflection. If the deflection was greater than that 0.02 millimeters, then you had to continue those roller passes and LWD testing until you met that criteria. And that would allow you to determine that maximum allowable LWD deflection. So some states and entities have gone and just looked at deflection itself and not modulus. And that's in an effort to get away from that A parameter and assumptions of Poisson's ratio and unit weight. So if you back it all the way out to just deflection, then you can kind of eliminate some of those extra variables. Another way to look at it is just based on stiffness, which includes the force. So we would definitely recommend with our device, since we're measuring that force every time, you could back it out and just look at stiffness and not modulus if you want to kind of eliminate that A parameter. So that would be one option. So that kind of gives you an overview and some of the details there. And now I'll turn it back over to Larry Olson for a discussion on testing on proctor molds.
Thank you, Pat. That was very excellent. And obviously shows his background both in research and practice using the LWD. So early in my career, I got bachelor's and master's in civil engineering and geotechnical from the University of Texas at Austin. And I worked locally in Denver for almost 5 years at CTL Thompson, doing geotechnical materials and pavement engineering. And my first year in particular, I got the chance, as most young geotechnical engineers do, go to the field and do quality assurance testing of the compaction of subgrade road base, even asphalt, used a nuclear density gauge, dug the sand cones, burned out moistures in the field, the whole bit. So as we got involved more and more in this, it just struck me one day that perhaps the way to get away from and make it a little more universal, doing the rolling strip compaction testing that had been done by Indiana, Minnesota DOTs and others, was to do the lightweight deflectometer testing on a proctor mold. And by chance, one advantage in the first case I've seen of English versus metric, a 100 millimeter plate fits almost perfectly into a 4-inch mold. An 150 millimeter plate fits almost perfectly into a 6-inch mold, much like a piston. So I had this idea, and I went over to a laboratory locally. I was at that time for 2011 to March of 2018, getting our Rockville, Maryland branch office going, and tested at the ECS laboratory, as you'll see in a minute, in Chantilly, Virginia. They were kind enough to do some proctor testing with me and for me. And there you see me at their lab with an earlier, larger, oversized plate at that time, testing on a 6-inch diameter proctor mold of a clay sand soil. Well, I shared this idea with Professor Charles Schwartz, Chuck Schwartz at the University of Maryland, because I knew they were just getting started in 2013 on a transportation pooled fund study sponsored by the Maryland State Highway Administration, their Department of Transportation, and 7 other DOTs contributed funding for $400,000 for a multi-year study to standardize, as it says, the lightweight deflectometer modulus measurements for compaction quality assurance. So Professor Schwartz and his students, 2 primary PhD students, Dr. Sadaf Khosravivar and Dr. Zara Afsharikia, were involved in that. And our LWD-1 was one of the LWD instruments used in the research. They also evaluated various moisture content determination methods, because you still need to measure moisture content. So this was an approach that made sense to me, because if you're measuring dry density versus moisture in a proctor anyhow with a 4 or 5 point curve, you still want to know optimum moisture content for compaction, quality assurance, quality control purposes, to achieve optimum density. But to do the same testing at the same time, after you would prepare the sample, you could even put the collar back on it, as is shown in the next slide. So this is what I did at their laboratory. You can see that the curve of dry density versus moisture content is shown in blue here, in pounds per cubic foot. Optimum moisture around 17.1%, around 109 pounds per cubic foot. But in this clay sand soil, on this 6-inch proctor mold, the stiffness peaks up and then drops as the moisture content increases, as you would expect in that type of soil. So it shows stiffness in kips per inch on the right. This is now, as Pat showed earlier, in the Young's modulus equation based on stiffness, soil type, and the radius of the plate. This is the plot of Young's modulus, same general shape, because there's just some constants involved, different there with Poisson's ratio. But Young's modulus is plotted in KSI units there as well, and it does the same type of shape of curve. So this looked very promising to get stiffness and modulus at the same time you were doing the proctor testing, not much additional time and effort. So you would, after you do your testing, you would then take it, do an oven dry moisture on the soils, and then proceed. So that led us to decide to develop over time a smaller unit to do some stress and strain compatibility matching, because originally the 10 kilogram weight on typical road base or subgrade, depending on the diameter of the plate, was designed to approximate the truck tire pressure that would go through a pavement and be on top of the road base or even the subgrade soils at the greater depth. So this lab unit is shown on the left. It's a shorter shaft. There is an option. You can have one unit, a tall field unit, remove the top shaft and put the lighter drop weight, which is only 8 pounds, dropping about 10 inches and generating about 400 pounds force. Again, the same equipment can be used. Now, if you're doing a lot of testing, you would want both a lab unit and field units. But one lab unit could then be testing on your proctor molds. So the field unit, it's been mentioned already, it's the 22 pounds, 10 kilograms, dropping about 2 feet, 24 inches. Typical field plate diameter is 200, 300. The University of Maryland preferred the 150 millimeter diameter, whether it's ASTM D698 or the modified proctor test, depending on the materials, because that was a little more consistent in a larger specimen for comparing and testing. So after they completed the pooled fund study, funded by the DOTs, the Maryland Department of Transportation and State Highway Administration funded a follow-on study for Dr. Schwartz and his 2 students at the University of Maryland. And that report's also available on the web, or we could get you a copy of it. But the final report was generated initially summarizing their pooled fund work, and that's here too. So this is the final report you can get for the pooled fund study. One of the things they did was they did the math, as you could imagine. When you're testing in the field, that's an elastic half space. It's not constrained, it's an unconstrained modulus, but it's a constrained modulus because you've got a proctor mold. So the equation is modified for calculating Young's modulus. It is the same Young's modulus and very similar now in stress levels for both the lab and the field by using the lighter drop weight and the shorter drop height. But Young's modulus then is rewritten in this equation for the lab test. So that's in our software, whether you're defining whether you're doing a test in the field or the lab. But it is the same, let me emphasize that, the same Young's modulus by using the appropriate equations. So this is just a plot of modulus in the moisture density curve again that we've been looking at. And this is more of a road-based material. It's much lower optimum moisture, around 6.5. And there's a fitting of the modulus curve shown there as well. So it's important that, like any project, you will be specifying a percentage of moisture range and also modulus range. And we'll talk about that concept. So this does show what I was referring to earlier. I've just got ahead of myself a little bit of how you have the smaller lab unit, and it's an aluminum drop weight instead of steel to be lighter. It puts out about 400 pounds of force. And as I mentioned, 150 millimeters is probably the preferred plate size to do it in a 6-inch diameter proctor mold. The unit is shown there. I would tend to do it with the collar in place. I put the collar back on it after I trimmed it, and gotten the weight, if you will, of the specimen, and then run the test. And that way you would get your dry density as well later, as you get a moisture content of a moisture content in the lab. But if you have the collar on it, that's going to constrain it. It won't tend to fall over, and it'll work just fine. So, but it's shown for ease of seeing everything there with the collar removed from the proctor mold. So what do you get? This just shows some results of a dry density versus moisture proctor compaction curve and the laboratory curve of Young's modulus versus moisture content as well. This is again in the software. So you've got a defined curve that your field personnel will be referring to for a given subgrade soil or road base for a given project. So they suggested 2 standards, and we're kind of adapting these ourselves, and we'll soon have our own version of these. But the University of Maryland came up with 2 standards, test methods. One is for laboratory determination of target modulus using the lightweight deflectometer drops on the compacted proctor mold. This is only a draft. It is not anything official by AASHTO yet. They wrote it in that general format. And this is the similar approach for compaction quality control using the lightweight deflectometer in the field. So 2 draft standards have been written in an AASHTO format by the University of Maryland researchers. The Maryland DOT then decided after this was done, they funded a follow-on study to compare the nuclear density gauge, designated as NDG, versus the LWD. So Dr. Schwartz and Zara Afsharikia came out and did a study, a follow-on study that was published in December of 2018, where they were testing on real projects, state highway construction projects, companion testing in the state of Maryland doing their normal nuclear density gauge testing, and it was compared directly with the lightweight deflectometer testing. So one thing is you do have to account for the underlying subgrade conditions. So if you're testing at a base level and you have a subgrade below it, there are equations where you correct for the modulus subgrade to get the true Young's modulus of the road base. And that's what this equation is shown here again, to get you the modulus. So that is something important to recognize. You can, by using this, then account for the true base modulus as compared to the lab, because there you're compacting and testing presumably on a steel mold on a concrete surface typically. So what did they find? When they did this, and I guess I should mention, if you wanted to, you could also do the 2-layer testing with 2 geophones for road base and subgrade, and that allows you to determine the modulus that way directly. But they've got this theoretical approach to doing that, and this is an interesting plot because now you're comparing the Young's modulus in the field measured to the target modulus from the lab. And so as it says, they've checked at 7 granular aggregate base sites, multiple tests of course, and 3 subgrade fill sites. And when you look at this, what you see is as a percentage of compaction that basically when it's to the right of 1, which means you met or exceeded your target modulus from the lab at a given moisture content. Notice I said something, it's important to know moisture. In the proper moisture range, like any compaction quality assurance control effort, that it also passed the nuclear density gauge testing. But when the modulus in the field was less than the target modulus, the nuclear density gauge testing also failed. And that's the real meaning of this plot for these different test sites. Again, this is all published and available. You can get it. We can give you a copy of it, but it is available online. So this was a very promising result that showed indeed, to summarize the study. So the lightweight deflectometer testing on the proctor molds is easy to get them to target Young's modulus in the lab for the road base and subgrade fill materials. And the ratio of the field measured modulus to the target modulus from the lab was a good criteria to assess the quality of the compaction as a function of moisture content. And the nuclear density gauge, percentage of compaction versus the E field, Young's modulus of the field divided by the target laboratory modulus, consistently showed where conventional nuclear density gauge test results with percentage of compaction and moisture content approach satisfied the MDOT State Highway Administration compaction specifications. They also had, as I mentioned, the ratio of the field to target modulus exceeding 1.0 higher and confirmed the validity of the LWD tests. So the overall conclusion is the lightweight deflectometer modulus-based compaction quality assurance approach can replace conventional nuclear density gauge based measures. Pat and I both want to thank you very much for your time and attention today. We'd be happy to provide any additional information you need. Send us an email. Some of these references we've listed. And certainly be happy to discuss. We're looking for groups that want to do some comparison testing. Again, like whether that's a university research effort or consulting effort that want to compare the nuclear density gauge with the LWD. Certainly, we've sold a number of units, increasing interest all the time. We are seeing that one of the early applications has been for the stabilized soils, because that's something where density alone is not what you want to see. You test right away, whether it's cement, lime treatment, or chemically stabilized soils. Then you test after the curing has occurred or the effect has taken place of chemically stabilizing them to see the increase in stiffness and modulus, which is what everyone wants to see. What they paid for is actually worked and been properly placed and performing. So with that, I'm just going to, this concludes the talk, but both Pat and I are more than happy to open the floor up to some questions. And thank you again for your time and attention today. And Pat, I have a feeling you'll be asked a lot of questions, so you come over here and we'll socially distance enough, we can both talk. So everybody stay healthy and we'll open it up to questions. Thank you very much.
The first question is, what is the effective depth for this Modulus measurement?
Yeah, Pat did some research on this.
Yeah, typically the effective depth, kind of the rule of thumb is 1 to 1.5 plate diameters. That was one of the things we looked at when we buried the stress and strain transducers in the ground, and the conclusions from that research were indeed that that's right in the ballpark to kind of the 1 to 1.5 plate diameters.
Okay, next question. How do we convert this to percent compaction?
You don't really convert it to percent compaction. The point of this testing is to recognize that modulus and stiffness really do matter, and you are trying to get to the target lab value or above. That comparison was done by the University of Maryland in that followon study I just closed with, where you exceeded the target ratio or equal or exceeded it, it also met the normal percentage compaction criteria. And that's what they were trying to show. So it's a different way of thinking of quality assurance or control of compaction, for sure.
Okay. How do you determine the Poisson's ratio to compute the value?
Yeah, that one is an assumption. You can assume a Poisson's ratio based on the soil type. That's the easiest way to do it practically.
And that number is often, I think, 0.35.
Yeah, between 0.3 and 0.4. The software lets you set that to kind of whatever you want. Oftentimes people will set it for one soil type and then they'll leave it for that. Any work they're doing with that soil type, they'll leave that alone.
Okay. Is it accepted in the United States to determine the percent compaction as a substitution of the cone and sand or the nuclear density method as an alternative?
The answer to that is it's starting to be. Both Indiana DOT and Minnesota DOT, with their control strip approaches, did use it for quality assurance of road-based compaction. But until this ASTM standard is approved, I'm on that committee, and Pat was on it earlier, for doing the proctor mold testing, that has to be done, I think, first. And then specifications will start to be applied. Any more to add to that, Pat?
Yeah, it's a chicken and egg problem where you can't do the testing without it being approved, and you can't get it approved without proving that it works. And so that's why Larry mentioned, anybody that's interested in pursuing this, DOTs or researchers, we'd be happy to work with you. We do think it's the way forward, but it has been slow to be implemented.
There is a lot of interest just because of the change in design of pavements in particular, where it is based on modules.
What is the maximum thickness of soil layer that the modulus can be determined for? I think you've already.
Now, it's a little bit of a function of plates. You want to talk about that?
Yeah, the plate size you can vary, like Larry said. Usually we use an 8-inch or 12-inch diameter plate in the field. There are several kind of criteria that go into selecting that plate. One is your lift depth, how deep you're trying to see. So if you're doing 6-inch lifts or 12-inch lifts, that may influence what plate diameter you want. The other factor is how soft the soil is. If you're doing really soft soils, that larger plate diameter lowers the force a little bit and can keep you kind of in the sweet spot as far as deflection measurement goes. If it's really soft soils and you go that smaller plate, you might be overranging the device. So stiffer soils, you might go to the slightly smaller 8-inch plate. We tend to prefer the 8-inch plate in general and find it to work for most things. But if you're on really soft clay, you might end up with a 12-inch plate.
Yeah, and the University of Maryland researchers decided to just make it simple and use the 12-inch plate in their follow-on study. But by measuring the force and measuring the displacement, as Pat indicated, either plate can work depending on the situation. Definitely, if it's softer, you should use the larger plate for sure.
You have to do a standard sand replacement test to calibrate this equipment.
No. But if it's too coarse at the surface, you will fill maybe I should ask for a little more clarification of the question, but I know you will fill the surface with like a white quartz sand, much like you do in the nuclear density gauge. It's very coarse, try and even out the application of the load. But sand replacement, the only other thing I can think of, you might be referring to the fact, well, maybe, but there's also when you get into some coarser materials, you get into some issues on the mold side, and there's some special things you have to do because they get to be too coarse. So maybe we can ask the questioner to clarify a little bit for us and see if we have a better response. In case we missed.
So the person who asked that question, either clarify it here or send us an email.
Okay.
All right. Has the LWD sensor been used or tested on roller compacted concrete?
Not to my knowledge, but I think it'd be an excellent application to check the stiffness. But as you know, what's really happening there is as the cement cures, it develops much greater stiffness. Any comments, Pat? When you're testing early on, it would be like, is this a good compaction stiffness that will lead to a denser, stronger RCC would be my comment. Because it's much like testing road base until it starts to cure.
Right. I think I'm not aware that it's been used that way. I think it is a good possible application. The one trouble may be if it gets too stiff, things that are really too stiff, you end up with just not enough deflection to measure. So that's when we add the additional weights to get a larger impulse load to try to get some, out of the noise level up into the measurement range.
And although we didn't show those weights, they're pretty simple to add on to the unit.
So there's a comment that said in Australia they have found that 1.35 times plate diameter is their best result.
Right.
And
Pat agrees with that. He also looked at those stresses with depth and it's sort of the zone of influence, if you will.
so here it says Professor Schwartz's study talks about developing a quadratic equation to fit the lab modulus curve. And what is the justification behind that?
Well, that's one of the things we're kind of interested to look at carefully ourselves with more studies, whether that's really necessary or not. It's definitely a good approach that they were using in their studies, but Pat and I want to see more data to decide if that part has to be done.
We would prefer a simpler implementation method. We think that would be more widely accepted to make it as simple as possible. So we're a little concerned that some of the recommendations there were a little too involved, but there is certainly excellent research and certainly something to take into account when we're trying to refine the process.
And if it does have to be done, we'll be working on the software to make it as computer-based as possible.
Have you done any comparisons with the Dynaflex sensor?
Well, the Dynaflex, Dynatest perhaps.
Well,
There is a Dynaflex.
There's one where you lean on it and measures the finger elements.
Okay.
That might be, but I'm not sure. So the short answer is no.
Okay.
But certainly one of our competitors is Dynatest, as mentioned in one of the slides. But maybe it wasn't. But in any case, the Maryland study compared Dynatest device, the Zorn device, and our device. You would see that readily in the available information. And they were plus or minus similar. The Zorn device does not measure the force. They assume gravity and the height of the drop to get their force, which is not so good. If you're testing on soft soils, it'll be less force. If you're testing on a stiff road base, it'll be more force from the same drop height.
Have you determined the effect of increasing strength of a soil cement layer?
We have a number of customers who have used it on stabilized soils of various kinds, whether it's lime or cement or that. I'm not sure I totally understand.
Yeah, typically the testing is done periodically right after the stabilization is performed. And so you kind of can plot that increase in stiffness versus, the hours after the process.
Or days, depends on the material. But normally they will have a normal time when they want to check it.
Are the true subgrade or base layer modulus values dependent on the in-place and or lab density and major content value? If so, how do you make the selection?
It really is driven by moisture range that you want in your compaction for optimum, plus or minus, and the modulus ties to that moisture content. So it's the kind of integrated by doing both the LWD testing and the normal moisture content versus dry density testing of a proctor curve. You want to add something further to that?
Yeah, so you will have to have a moisture content measurement in the field when you do the LWD testing, so that you know what that moisture content is when you're doing the testing. If that's involved right there, you know, immediately after compaction, oftentimes you're doing that moisture content to ensure you're in the optimum range during compaction.
Yeah, the University of Maryland and others have looked at various approaches to doing the field moisture content in the field. Obviously, people are using nuclear density gauge, but then you're still using the gauge. But they also looked at the OHAUS, OHAUS moisture meters. They thought that was better. They checked some other things out. Indiana DOT, I talked to them recently. They've looked at the OHAUS moisture meter. They actually are taking the samples back to the lab and doing an oven dry moisture. So it delays it until they can get that oven dry moisture. But one way or another, they will end up with moisture.
Can you use the LWD sensor on a compacted sand without gravel?
Yes, that's not a problem. You tested some sands like that, I think.
Can the LWD method be used for rock fill?
Rock is where Larry mentioned briefly there a second ago about when it gets really coarse, you end up with more variability. And so oftentimes what's done on a coarse rock, you know, if you have aggregates that are 1 inch plus or 2 inch or larger, you would put in a sand layer on top. So you put 1 inch of sand on top of that rock just to even out that stress distribution from the plate. Otherwise, we end up getting kind of point contacts in the plate, and you get much highly variable results. So having that sand layer on top of the rock has proved to be important. This again is an ongoing layer or ongoing area of research. It may also help to go to that larger plate. Get the ratio of the plate being larger than the aggregate size helps. But then of course you're lowering the force because you're spreading that force out across a bigger area. So that's when the heavier weights come into play.
Yeah, I'll mention, and Pat knows this too, Professor Mitra at Oklahoma State University was awarded a grant by the Interlocking Concrete Pavement Institute to look at the very coarse drain rock, very similar to railroad ballast that they use under their pavements to check the compaction using an LWD approach. And we have a consulting role of supporting him in his research, but he's just starting that research recently. And so some interesting things may come out of that as well.
People want to ask the question.
Okay. Well, he also is going to explore a larger diameter mold. I think it's nominally 12 inches in diameter. So a much larger mold is something he's exploring.
Can you make measurements on concrete slabs?
Again, typically they're too stiff, but we get very small displacements, so you get down in near the noise level. So it depends on how thick the slab is. The short answer is no.
We do another test called slab impulse response, either an impact echo for thickness of the concrete slab, as well as checking for voided lack of subgrade support, poor to questionable below a slab on grade. And that works out to 12 to say 18 inches thick. And we combine that with ground penetrating radar if you're after, is there good subgrade support or not. But the advantage of the impulse response test is very similar to what we're doing, but it's a handheld 3-pound hammer with a geophone, and it will handle that excitation better because of the sensitive nature of the measurement. And you can see very thin voids below a slab of less than a 1/16 of an inch. That test for radar typically takes at least a 1/4 inch, if not a 1/2 inch, to see the air gap.
Why does the peak displacement not align with the peak force load on the data filters?
Yeah, so there's a leg there based on the way the soil, the dynamics of the soil. That leg will depend on the type of soil, and so the peak displacement occurs slightly after the peak load. as we've shown in our slides, the analysis method right now just takes those peak values and sticks those into the equation. There's certainly, it's another area I looked at in my research, room for improvement in the analysis method. It's a dynamic loading on the soil. It's soil dynamic loadings are complex, and we do take the full time history of the data. So we have time history of force and displacement. Those can be easily exported from our software. So if there are researchers out there looking to explore different analysis methods and they take into account the full waveforms there, those are available from our software.
Someone wants to just go over what your moisture source is again.
To measure moisture, the University of Maryland study looked at Decadon type devices. They looked at the O-house meter, which can do it in about a half an hour in the field. Indiana DOT has used that as well. But Indiana ultimately decided, there's pros and cons to the O-house. They ultimately decided they would do an oven moisture content. And the problem with doing a microwave or burning out in the field is you start to have issues with not getting the accurate moisture. There is a correction factor they applied even to the O-house of about 11% to agree with an oven.
And then somebody asked you to repeat your comments about the advantages and disadvantages of the different LWD models.
Well, we have a biased opinion there. The reasons we like ours, number one, we measure the force. We think that's important. Two, we use a geophone to measure the displacement to minimize the integrations through a single integration. Three, we use a steel spring. It's less temperature dependent. We get more consistent force.
Doesn't really age over time.
Right. We like that our unit's made of stainless steel. It's not plated as some of them are. It's all stainless steel and aluminum. It's very durable that way. We like that our spring is in the weight. We think that's a unique feature of ours that creates a cleaner impulse loading on the plate. There's some ergonomic things we prefer about ours. Those are kind of the main features that we appreciate about ours. Also that it's made here in the US.
And certainly to emphasize it again, a number of researchers, Pat, subsequent students of Mike Mooney's, Chris Sensony, and others at Colorado School of Mines, University of Maryland, are all pretty confident you're better off measuring force, if you will get a more accurate result than just saying you know the drop height and you know the weight, the impact force because you know the drop height of your weight. That varies depending on what's springing back at you. Soft soils, it will be low. If it's high soils, stiff soils, it will be high.
So someone here says they basically tried this 20 years ago in Europe, and it was still a chicken and egg problem then.
Well,
they're ahead of us, but yeah.
I think that you will see this come forward because of changing the design to where Modulus matters. That's probably the simplest way to put it. There's definite interest at all the DOT levels. 8 DOTs kicked in the funding. We've got to get the standards out there, whether that's ultimately an ASTO spec or ASTM specs to account for this. But as the University of Maryland study showed with the follow-on study, it is definitely, their conclusion was that it is definitely a very real replacement for doing nuclear density gauge testing in the world.
The last question was, can you use this on asphaltic concrete?
A little bit of work has been done with a very small contact area on asphalt. That, again, is a research topic. There's a better chance on newly placed asphalt of checking its stiffness, but very limited work's been done on that yet. It's similar to the concrete problem, but not as stiff, so maybe it'll work with a very small contact area, like between 30 and 50 millimeters, maybe, for the base plate.
All right, that's it.
We want to thank you again. And Pat and I certainly appreciate all the questions, and like I say, be happy to reach out to us. If you have any more, we'll be more than happy to support you. So have an excellent day, and as they say, stay healthy.